Today, we introduce a simple project about building a capacitance meter using an STM Nucleo board. A capacitor can be compared to a bottle with water representing the electric charge. The current acts as a flow that gradually fills the bottle until it reaches maximum capacity. When current flows into a capacitor through a limiting resistor, the voltage across it increases in a non-linear exponential manner. This characteristic allows the capacitor's value to be calculated by knowing the resistor's value and the time it takes to charge. We hence experimentally charge a capacitor to verify this. Following the shown diagram, the arrangement comprises of a battery, a known value resistor, and the capacitor to be tested. The resistor controls the entering current into the capacitor. As the capacitor is depleted, its potential difference is first 0 volts, until the voltage across the capacitor equals the battery voltage. Activating the charging process shows an exponential rise in the voltage. By connecting the two capacitor terminals through a protective resistor, pressing the button rapidly discharges it. One can thus repeat the charging process. We address an electrical connection between several components rather than an electrical circuit schematic. The STM32 Nucleo F411RE development board, a 10,000 ohm 1% resistor to limit the capacitor's charging current, and an unidentified capacitor C whose capacitance is to be measured. While the capacitor's value between 100 nanofarads and 10,000 microfarads is unknown, the resistance and input voltage are set. The digital pin D2 is linked to the 10,000 ohm resistor and charges or discharges the capacitor. High supplies 3.3 volts power to charge the capacitor across the resistor, while low reduces the capacitor's discharge. Connected between the resistor and the capacitor, the analog input pin A0 lets the board read the voltage across the capacitor. This voltage reading computes the duration to attain a given voltage and indicates the charge level. Digital pin D2 is set to low to guarantee the capacitor begins at a specified voltage level, therefore providing a connection to GND and discharging the capacitor to 1 volt. D2 turns to high once depleted to start the charging process. The board tracks the capacitor's time to reach 2 volts. This is the project's most critical aspect. Normally, the time required for a capacitor to charge from 0 volts to 63% of the maximum voltage is measured. This percentage, derived from mathematical analysis, is a conventional value representing significant progress along the exponential charging curve. However, this project uses a slightly different method, measuring the time it takes for the capacitor to charge from 1 volt to 2 volts. The formula used differs from the classical one and is derived from curve fitting on electronic simulations. Now let's see how to use the capacitance meter practically by measuring an electrolytic capacitor of 2000 microfarads available in the lab. To measure the capacitance, simply connect the unknown capacitor to the respective contacts, as shown in the previous circuit diagram, ensuring correct polarity. Press the black reset button on the board to start the firmware execution. Initially, pin D2 is set to low, slowly discharging the electrolytic capacitor as shown in the graph. At this stage, the onboard LED is off. Once the capacitor's voltage reaches 1 volt, it starts charging to 2 volts. The charging process is indicated by the onboard LED lighting up. After a few seconds, depending on the capacitor's value, the results will appear on the serial monitor, which can be replaced by other serial plotting software on a PC. It is entirely normal for repeated measurements of the same capacitor to yield slightly different readings. It is recommended to repeat the measurements several times, for example 10 times, and calculate the arithmetic mean of the collected data. With some hardware modifications, particularly to the firmware, an LCD display can be implemented to show the measurements.